Howdy, I'm Kate Davis from Texas A&M and I'm the PI for this project. We call our project CYPRES for Cyber Physical Resilient Energy Systems, since that's the objective of CYPRES is to enable resilience in cyber physical power systems by creating a new energy management system that is truly cyber physical and inherently considers security.
The reason this is needed is that advanced cyber threats can target physical power system impact, and defending against these requires taking advantage of both cyber and physical data and models together, which is very different than the way systems are operated now. So CYPRES's approach to cyber physical resilience actually begins very early before an event occurs in the planning phase. So at this early stage, our approach is improving cyber-physical situational awareness, which includes modeling and performing preventative risk analysis of what is possible. The outcome that we are targeting from the CYPRES project is shaping what resilient grid operation would look like when we consider the system as the truly cyber-physical system that it is, by finding out how to make the energy management data flow process inherently consider cyber state along with physical state. And CYPRES, this new system, is intended to provide cyber-physical grid analyses over the entire life cycle of an event. So to address how to prepare for, endure, and respond to events, as well as closing the loop to learn from these events and plan the system better. So actually, this resilience lifecycle approach is really important for grid cyber-physical security. And in fact, the importance of security for power systems is entirely driven by operational reliability and resilience. So the feasibility of CYPRES is supported by our use of well-known industry-used data sources, coupled with our team's strong background and our analytic foundations that form analysis components and modules in CYPRES. So this is the CYPRES model and envision workflow, and we can talk about it from left to right. So on the left side are data sources and major inputs to the model. These alerts and data sources feed into and are managed by existing commercial databases and tools. Then these existing commercial databases and tools feed our modeling and workflow solution. So these inputs go into a mathematical model generator and manager. And the top left portion of this diagram is the offline risk phase. So from the offline cyber physical risk, we get a list of high impact and low cost access paths. And then in the online phase, we fuse cyber and physical data, and we want to do cyber physical anomaly detection to estimate compromised devices and access paths. And then both of these together go into what I call an online cyber physical risk analysis module. And what we want to do here is estimate the proximity to high impact paths. And then both online and offline models and tools go into risk management and mitigation. And so here we want to use cyber physical data and models to recommend control actions that couple cyber and physical spaces, as well as do visualizations that are specific to different user roles. And so an example of this would be a list of actions to avoid potential attack impact, for example, by cutting access to high impact paths and controlling redundant devices. And so this is how we define success in the CYPRES project, which is by avoiding attack impact.
The purpose of this demo is to show how to combine cyber-physical models with online data, since the idea is that by using knowledge of the network combined with sensor data, further essential cyber-physical analysis becomes possible. And so we're going to show some examples of what that looks like in our demo today. Next, let's talk about the scenario that you will see demonstrated in our testbed.
So the topic for today will be reconfigurable networks to secure power grid. The primary objective for this demonstration will be how we make use of the cyber physical case to first model our physical system, then create the cyber topology using a core emulator. And once we create that cyber system in the core emulator, we would use the DNP3 protocol for controlling the grid using the DNP3 master component. And in this cyber network, we would build a few cyber intrusions, as well as once those intrusions are there, how we can misoperate the grid when the master gives control commands that we will demonstrate. As well as once those intrusions are done, we will make use of intrusion detection system to reconfigure our network in such a way that the under attack stage also the master can give proper control commands to the outstation.
So in the core network, we had one node PC2A in the 192.168.0.1 network compromised. And on this node, a man-in-the-middle attack using ARP cache poisoning was performed. First, in the man-in-the-middle attack, the ARP of the router is compromised, and it associates the IP address of the outstation with its own IP address, so that all information will flow to it. And in the second way, the outstation has its ARP table also poisoned by saying that the gateway is its IP address. So now it's in the middle of the communication and can sniff all the packets. As you can see, traffic would normally flow from the router to this outstation, but during the attack, the information will be rerouted so that the adversary is in between. And this will allow the adversary to not only sniff traffic, since DMP3, which is being sniffed, is a clear text protocol. It'll also have the ability to modify any measurements, close a breaker when it's supposed to be opened, or change a generation value if it wants it to be lower or higher, and then send that along to the outstation. You'll also get the response from the outstation and modify it so that it's a proper response that the MCC master is looking for.
Cool. And we can also create network congestion, distributed denial of service attacks if the adversary is inside the broadcast domain. Okay. So this is the cyber topology where there is a main control center interacting with the substation 3, substation 1, and substation 2. This one, substation 3, we showed the node which is already compromised, and all this data coming from the substations are going through using this path. So substation 2 communicates directly with the main control center directly, and substation 3 is also communicating directly. But the substation 1, they are having two paths to the main control center. So our objective would be to, if we compromise the substation 3, and we have a priority path by which the main control center connect with substation 1 using priority 1. So under the compromised state, we want to reroute this traffic, not through reroute this traffic to through the substations 2 instead of substation 3. And also, once we reroute, we can give some control command to the substation 1 to protect the grid even if the substation 3 is compromised, and also protect the substation 3 after we reroute the traffic. So in that case, we can protect substation 3 as well as substation 1. So for detection and response, for detection mechanism, what we have used, we have made use of Snort intrusion detection system. It is a very widely known IDS used in industry. There are various preprocessors written for ARP cache poisoning, DNP3 based payload modifications, as well as some distributed denial of service attacks. So we would make use of this, but there are lots of alerts as well due to this Snort. So we want not only to make use of Snort, but we make use of some other resources, for example, the TCP dumps. Unlike in other testbed where we are running simulator, it is hard to run this intrusion detection system, but since we are running core, we can make use of the Linux containers inside the core to run any application real time. And we also make use of IP tables firewall rule to protect the broadcast domain by running them in the routers that I showed in my previous diagram. And we also, there is a way we can make use of Splunk, Javix, packet bit in our platform to do the network monitoring for the system. In this demo, we are not showing, but we have implemented in some of our previous work. For the response, what we do is like we take the Snort alerts, TCP dumps, and we build our logics to either change our firewall configuration if they are under compromise, or reroute the traffic, as I mentioned in a previous slide, like change from priority 1 to priority 2. There can be multiple other responses, such as if that outstation is compromised, we can either isolate that outstation from the communication network and control physically going to that relay, or controlling directly the generators at that control room, rather than controlling it through the master, which is somewhere far from the outstation. So in a Snort, basically we capture the traffic, then we do the decoding we are doing because there can be ARP traffic, DNP3 traffic, and some other background traffic such as HTTPs, but we are concerned based on what packet we want to decode. So in the Snort configuration file, we could enable which packet we want to decode, and once we decide those packet to decode, we could run some preprocessor. The preprocessor would help us to narrow down the search space on the protocol headers that we want to look into. So there can be so many features in any packet, but we want to make sure that those features which are more critical, we use it. And finally, once we pre-process those packets, we send it to the detection engine, and the detection engine will be based on what rules we feed into this detection engine. So in a real network, there can be multiple rules that we feed into, but that can slow down the operation of Snort if you have more number of rules and more number of pre-processing to do. So in our demo, we haven't used a lot of rules, but there are 6 to 7 rules, I think, that we are feeding into this detection engine for this demo, but we could scale it up for more. And once we feed those rules, we'll get those real-time alerts, and we'll make use of those alerts along with TCP dump to make our decision making to either reroute or make use of firewalls, or maybe manually operate the grid. So basically, rules-based operation will work when there is attacks which are well known previously, because we would be defining the preprocessor for them beforehand. But there can be some 0-day attack which we cannot detect by using this Snort-based IDS, for which we may make use of inferencing techniques, so pure data-based solution for. So we build the network with core and create in the Firewall Dynamic Studio. And once the substation router in the core is compromised, we are basically compromised the Firewall Dynamic Studio, because we can give malicious commands or measurements we can modify. So let's say there is a Snort running in the substation router, and it detects that there was some compromise. And we also collect a TCP dump from that substation router. And this Snort, as we are running a couple of rules, which where we are doing DNP3 pre-processing, DOS ping flood, ICMP ping flood pre-processing, as well as ARP spoof ping processing, we get alerts related to them. So along with those TCP dumps and this Snort alert, we feed that to our response engine. And this response engine, we also feed the current firewall configuration, current routing table, as well as the current ARP table. Based on the status coming from the Snort, as well as the current firewall rule, routing table, and ARP table, we modify the firewall rule, routing table, and ARP table. And we validate this new configuration before we feed that into the core router, where we run the substation router, which was compromised by ARP spoof attack. And once we recover the network, we will recover the physical grid.
Okay, so first I will run this DS Federate, which is a DS client, which will be used to connect to the DS to get the data. It's also helix federate so that it can publish the data to the helix subscribers. So I will run this one first, and then I will run the gRPC server, which will generate the core network. So this is the topology we are using NetworkX to show the topology of the network that we built within the core. And then we will run the gRPC SCADA. And then we will run the gRPC SCADA, which will run the outstation scripts in the in 3 PC nodes, and also run the main control center script.
We can see that in the PC2A and PC3A and PC1A at the terminal, we have instantiated the OpenDNP3 outstations, and we run the OpenDNP3 master in PC0A. So we can get the generator, load, and branch status for the outstation in 192.168.2. We can switch to other and see. So as we showed in our slides, that the substation, the bus number 2 is in substation 192.168.0 network, 3 and 4 and 192.162.1 network, and bus number 1 is in 192.168.2 network. So what we would do, we will give some commands from the master to see whether they are operating or not. So we'll go to 0 maybe, and open the first branch. We use the OpenDNP3 direct operate. So when we click on that, let's go and see. We could open that branch. Similarly, we could try some other control commands and see. Maybe, yeah, let's close that one maybe. Yeah, let's close that one, and that we can also. Okay. Okay. Yeah, we do the attack now and see, run the gRPC adversary. So we are running the Wireshark at the router R0, R1 and R2. R2 is the compromised router, and R1 is rerouting router that we'll use in our case. So we filter the traffic for DNP3 so that we can find it easy to troubleshoot. Okay, let's give a command now under compromised state. We'll give a close command to this. Close command. Let's see. So we gave a close command, but we open the line, and that causes the line overflow between line 2 and 3. Now we'll run our protection system by reconfiguring the network, and let's see whether we are able to reconfigure or not. Wait. Okay. 192.168.1, we're going through the router R2, but now we'll see they all will go through router R1. So what we'll do, we'll give a command to 1.11 to reduce the load, reduce the generator. So we'll go to index 0 and go to the analog box. So uncheck that one and go to the analog box, make it 45 and activate. Okay, let's see. So we can see the generator is reducing, and so as we are able to reduce the line from 2 to 3. But now the command that went through, it went through a different route. So we can see in the Wireshark. Can you go to the Wireshark? No, not in, yeah, this one. Let's open the Wireshark and see. Can you filter like based on 1.11? So right now all the traffic is going through this router. Earlier it was going through the above router. Yeah, if you scroll up. So you could see 1.11 was the traffic that was going through the compromised router earlier, but now we got into the non-compromised router. So we were able to give, but still our outstation with 192.168.0 is still compromised. So we want to protect that, and we can see, can we protect, have you protected or not? Can you give another command to 0.10? Yeah. So it's false, right? So we'll try to close and we'll see if we can close it or not. Let's see. Oh, so we were able to recover the network. So you saw in some time back that we were not able to give the command, but now we recovered the network and we can able to control. So now we basically rerouted the traffic for the substation in the network 192.168.1, as well as we protected the network in 192.168.0.